Video on game theory, and unfortunately, we don't have the time in this class to get too far into game theory, but it's a really interesting topic, and I think there may be in the Division of Applied Social Science a class all on game theory, so I would recommend taking that if you find this interesting. Really, the only part of game theory that we're going to get to talk about is suppose you have a world where you have two decision makers, and their decisions will jointly influence what outcome happens and therefore the payoffs, right? So you have maybe two companies that are competitors in a market. Well, up until this point, we've thought about only profit maximization from a one-person perspective. If I know my costs and potential revenues, how can I maximize profit? But here, we're starting to think about a world where it matters what your competitor does as well. So this sorts of game theory problems that we're going to analyze, you have multiple players who know exactly how many players are in the game or how many decision makers, what are the possible strategies or actions that their competitor could take, and then based on that, they can figure out what is the best or profit maximizing decision that their opponent can make, their competitor, and what is the profit maximizing decision for themselves. Right, so in the real world, companies don't always know all of this information. They may not know what exactly their competitors' profits are going to be or what their profit maximizing decision would be. So it's a little bit simplified, but nonetheless, companies do think about what is the competitor going to do, and based on that, what should I be doing? So this is basically the underlying game theory. So what are the components of a game? We have a number of players or decision makers in the game. We have information, which in our games, again, we're going to have games of perfect information, meaning that our players in the game know all of the strategies, all of the possible outcomes based on what strategies are chosen, and what the payoffs are of the combinations chosen. There are a couple of assumptions that we're going to make about decision maker. First of all, that preferences are clearly defined. The objectives of each player is well known. And that objective is to choose rationally to maximize payoff. Right? So if we're talking about companies, we're talking usually about profit maximization, or we can have these little two-player games, which we'll introduce here, where each player is trying to maximize their payoff as defined by the setup of the game. All right, so rationality in game theory means that each player is choosing to maximize their payoffs at all times. So we start again with simultaneous move games. You have usually two players making their moves at the same time, such as offense and defense in a soccer match here, but that's not really true because this is happening over time and they're making multiple passes. Maybe you could think about it as like a penalty kick. The kicker chooses to kick a direction, the goalie chooses to dive a direction. Those decisions happen at about the same time. So maybe that would be a better example. But we can illustrate these types of games where moves are made simultaneously in a game table. And then the analysis method is going to be best response. So each player is going to select the best response or their payoff maximizing response to every possible move by the other players. The outcome which is selected as a best response by all players is a Nash equilibrium, and there could be multiple Nash equilibria depending on the game. So sometimes in words, these sound a little bit more complicated, but let's just do an example of how to solve these. So suppose we're given a game table. All right, player one is listed here on the vertical axis, and player one's payoffs will always be represented by the first number in the box. So what this is saying is that if player one picks strategy one, and then we have player two here, and player two picks strategy one, then player one will get a payoff of 5, and player two will get a payoff of 9. If player one picks strategy one, and player two picks strategy two, player one gets 6, player two gets 15. Right? And so on. If player one picks strategy two and player two picks strategy one, we're here. If they both pick strategy 2, we're here. In each case, player 1's payoff first, then player 2's payoff. So how do we go about solving this using best response to find the Nash equilibrium? We have to consider for each player in the game, what is their best response to the other player's possible strategy? So let's think about player 1 first. Suppose that player 1 knew that player 2 was going to pick strategy 1. And so we can ignore the right column for strategy 2. If player 1 knows that player 2 is picking strategy 1, then they would get 5 for also picking strategy 1, and player 1 would get 8 for picking strategy 2. So conditional on player 2 picking strategy 1, what is better for player 1? It's better to pick strategy 2 because 8 is more than 5. Well, what about if player 2 was going to pick strategy 2? In that case, player 1 gets 6 for picking strategy 1, or 10 for picking strategy 2, is better off picking strategy 2 once again. And this is what we call a dominant strategy. No matter what player 2 does, player 1 is better picking strategy 2 than strategy 1. So when a player has a dominant strategy, a rational player will always play this dominant strategy because it results in higher payoff no matter what player 2 chooses. All right, so once again, let me just explain that quick. There's, I think, ultimately maybe 1 to 2 matrix solving types of questions or Nash equilibrium questions on the midterm, so it's worth thinking about here. Again, we're just asking, ignore the right column. If player 2 picks strategy 1, should player 1 pick the top or the bottom box? Strategy 1 or strategy 2, they're better off picking the bottom because player 1's payoffs are the first ones. 8 is higher than 5. Right, ignore that column and look at the right column. If player 2 picks strategy 2, what's player 1 better off doing? Also strategy 2 because 10 is more than 6. All right, so for player 2's decisions, now we need to look at the second payoff. And we can ask if player 1 is picking strategy 1, we know we're in the top 2 boxes. Is player 2 better off picking strategy 1 and getting 9, or strategy 2 and getting 15? They're better off picking strategy 2. What about player 2? If player 1 is picking strategy 2, then player 2 gets 5 for picking strategy 1, or 12 for strategy 2, and is better off picking strategy 2. All right, so player 2 also has a dominant strategy to pick strategy 2. 15 is more than 9 if player 1 is picking strategy 1. 12 is more than 5 if player 1 is picking strategy 2. And so we would say it's rational for player 2 to pick strategy 2 no matter what. So what is the Nash equilibrium? We have this overlap of best responses here, and each player will pick strategy 2. The Nash equilibrium is the strategies chosen. So player 1 picking strategy 2 and player 2 picking strategy 2 is the Nash equilibrium. The payoffs in the equilibrium are 10 for player 1 and 12 for player 2. Right, a Nash equilibrium occurs when all players in the game are using an optimal response in response to all other players' strategies. So that's what we saw in the last part of the game. Each player picks the best response. Once a Nash equilibrium is achieved, no player can do better by changing their mind unilaterally. So from here, would player 1 want to pick strategy 1 instead? No, because they would get 6. Would player 2 want to pick strategy 1 instead? No, they would get 5 instead of 12. So neither player has an incentive to deviate. And even though the Nash equilibrium maximizes payoffs conditional on the opponent's play, it does not always maximize payoffs in the game. So we'll see an example of that. Maybe let's come back to this and do the prisoner's dilemma. The prisoner's dilemma occurs in this type of games when we have a single Nash equilibrium, which is inferior to some other outcome. So again, the Nash equilibrium of a game does not always result in the best possible outcomes. These prisoner's dilemma can occur in international trade, political campaigning, legal disputes, other types. But let's have a look. We have two companies, Target and Walmart, and they can either do, it looks like, heavy advertising or light advertising. The setup of the problem doesn't really matter so much. The prisoner's dilemma is about the strategies and the payoffs. All right, so let's take a look. Let's look at Target first. If Walmart is choosing heavy, is Target better off choosing heavy or light? They're better off choosing heavy. If Walmart is choosing light, is Target better off choosing heavy or light? Once again, heavy. So Target has a dominant strategy to choose heavy advertising. What about Walmart? If Target is choosing heavy advertising, is Walmart better off choosing heavy advertising and getting 50, or light advertising and getting 30? Once again, heavy. And conditional on Target choosing light advertising, is Walmart better off choosing heavy for 120 or light for 100? Once again, heavy. Walmart has a dominant strategy to choose heavy advertising. As a result, our Nash equilibrium each chooses heavy advertising, and they get payments of 50 each. You can see that this is not the best possible outcome. The best possible outcome would be, in this case, light, where they each get 100. However, if either one of them unilaterally chose to deviate to light advertising, they would get less, and the opponent would get more. So there's no incentive to switch away from this Nash equilibrium. So this is, once again, the prisoner's dilemma. There's a single Nash equilibrium achieved using dominant strategy, but it is not the best outcome in the game. All right, again, these prisoner's dilemmas are used to model all sorts of situations. And so it's a very simplified version of the real world. But once again, we're sort of working towards models which can try to understand and model decision-making in a more complicated sense. So cooperative outcome could lead to higher payoffs for both players. How can these players get to this cooperative outcome where they're each choosing light advertising? Well, in repeated games, these Nash equilibria, these prisoner's dilemma with a single Nash equilibria, can be shifted to the cooperative outcome. We have another example here. You should come back and maybe make sure you can solve this on your own time. I don't want this video to go on too long. All right, but suppose we have this prisoner's dilemma game here. We have a dominant strategy, Nash equilibrium, which is not the best outcome for both players. In this case, cooperate would result in the best outcome for both players. So the question is, how can this be achieved, especially if this game is repeated over time? And I think, here we go, we have some strategies here. It is possible to result in the cooperative strategy if the game is repeated over time and players are able to understand the moves of other players. So there's a couple types of strategies which could result in the cooperative outcome over time. Again, these ones are not, for my test questions, I really just want you to understand, first of all, what is a best response? What is a Nash equilibrium? And then you might have to solve, I really don't think I make you solve more than about one of these games. So just make sure that you're kind of familiar with these box solving problems. Okay, this is a topic in particular that is very difficult to condense down to a short video. I really don't want to go on more than about 10-15 minutes. I'm not quite sure how long it's been at this point. So I am just going to stop here, but if you want more examples, more detailed breakdown of these topics and how to solve these problems, or what exactly I'm going to be looking for in exam problems, don't hesitate to reach out.